Welcome to the Null Labs, where we explore software engineering. So let's learn something new. Do you all know what hash maps, ART, BTrees, GIN, SS tables, BRIN, LSMTrees, and even your local library all have in common? Well, if you don't, you might want to stick around and learn what all these different things have in common and how you might even leverage them in a database. Well, enough of the trivia for now. Who here is ready to log yet another entry into our database discussions? Get it? Log, right? Okay, anyhow, as you probably know, we have been building a database. Now, not one to use. I'm looking at you. I mean it. Stop it. I see you trying to use the NullDB in production. This database is one to learn about database technologies. And currently our database has a huge problem. Before this and the next episode, if the database was just a mere 50 gigabytes in size, that's not a very large database at all. Our average read time for a value is over 31 seconds, but it gets worse. It can be as slow as a minute, and it can actually also be as fast as a millisecond. First, let's be honest here. At 50 gigabytes on this machine, we should be able to access any record in less than a few thousand nanoseconds. Realistically, we should work to minimize the impact the size of our database has with how long it takes to access a record. And yes, we should only be talking a single millisecond as a worst case P quadruple 9. And if you stick around for the next episode, we might actually get our database beating a millisecond at over 50 gigabytes. Another issue here is that every read should take close to the same amount of time. While there is always going to be some variation when you get data from disk, it should not be nearly this much. The more consistent, the better, and the better you can understand the load that your database is actually going to be able to handle. But then even then, we need faster reads. I can swim faster through a river of molasses and retrieve a value written on the inside of the bark of a tree before this database could return a value. I'm not even joking. And I know what you're thinking. I thought that log-based databases were blazing fast, right? I mean, we don't block reading of any value at this point, and everything is immutable. It should just be blazing fast, right? Inserting data is blazing fast. So why does it take so long to retrieve values? Let's walk through the access pattern we have right now to try to better understand our problem. Right now, when a request to retrieve a value by key is received, the very first thing we do is check the main log. If the value is not found in this main log, then we check the latest log file that was written to disk, reading it and scanning each line of our log file for the key. If at this point the record is not found in this log file, we will check the next log file. Each file we check, we read the file off of disk, and then we iterate over each line in the file, checking for the key. It's just exhausting explaining it. So do you see where this could be a problem? We don't even know if we have a value at all in the database. All we can do for every single request is search the entire database for the key. Remember, our access pattern is actually intentional as our data is stored on disk in a log. This means that by definition, we have to access data on disk in this way. It's actually a feature and not a bug. But like with all good features, sometimes they have drawbacks that you have to deal with. And right now, our biggest problem, while we can write blazingly fast, we can't find a record to save our lives. You have all probably guessed what we're going to talk about today. That's right, it's indexes. Indexes are pretty much just that, a way to actually physically find data on disk without opening random files and checking them randomly. And I know what you're all thinking. Did Merrick really say local library at the start of this video? How is that related to database indexes? Well, you just stick around. I think too often these indexes have become an abstract idea that people don't realize what is happening in the back end. And so today we're going to learn about database indexing basics. So let's build a list of things we would like to support with our index. Probably the first one everyone's going to think about is that we want to have the ability to quickly find a value on disk for a given key. The faster, the better. Constant time is best, log time is second best, and linear time, commonly denoted as O of n, is really not acceptable because file access is expensive and databases tend to have millions to billions of records in them. Let's say that the second goal of our index should be to minimize the amount of unnecessary disk reading we do have to do. I'm not going to say completely get rid of it, but the less the better. So if we access disk, it should be to actually retrieve a value. Otherwise, it's really slow and we're just wasting time. And we have proved just how slow it is with our current implementation. Another thing that we might like to do with this index is obtain groups of data or ranges of data. For example, you would like to be able to select all values between H and Y or between 50 and 100. Whatever the key might be. Now, a quick note before we jump into some of the technologies that power the world's indexing needs. I do all this work live on Twitch and here on YouTube. So if you want to join the live streams or review the VODs of the past ones that we've done, the links to those are in the description. So back to databases. So do you remember at the very start of this video, I asked you what hash maps, BTrees, LSMTrees, and actually quite a few other things including your local library, had in common. If you said database indexes, you would have been correct. Gold star for you. For brevity, today we're only going to focus on the aforementioned three. Of those three, do you know which one is used in everything from your SQLite and Postgres all the way to your blazing fast NoSQL databases like Aerospike? Now, if you had the bravery to say BTrees, you would have absolutely been correct again. 2 gold stars for you. BTrees, or some derivative thereof, are the tried, true, and tested database indexing technology out there. LSMTrees and SS tables are kind of the new kid on the block, most notably used in Google's Big Table, Cassandra, and ScalaDB. Though if you all get me to do a deep dive implementation, you might notice that SS tables actually leverage a bunch of other technologies, including BTrees, to solve some of their issues. But more on SS tables later. Hash maps or hash-based technologies, on the other hand, are not used in many databases. In fact, the only ones that I know of off the top of my head are the Bitcast storage engine, Redis, and Memcached. Though I'm sure there are others out there, I just don't know them. In fact, leave a comment with your favorite hash-based database. It would be cool to learn some more. Now again, this is not an exhaustive list of each index technologies. These are just the big players, and maybe, if requested, we can explore other, more unique indexes. But for today, we will explore just these 3 a little bit more. So for each record in our database, we want to store its location on disk. Well, if you really think about it, a hash map seems to make total sense, right? We want to have a key, and for that key in constant time, we would like to be able to look up exactly where the value is on disk. If the value of the hash map were to keep track of the log segment or even the line and byte offset of the actual data, meaning we wouldn't even have to scan the file line by line anymore, we could accomplish exactly what we want. This sounds awesome. This sounds exactly like we want. But it turns out hash maps are not commonly used. But why? Why? Hash maps provide some of the fastest reads of single values. Hash maps are also really simple to implement as an index in our database. Hash maps also play really well with our log-based data plane as well as our compaction. So why, I ask you, do you not see them used more? Why does it not dominate the database indexing world? Why, for the love of all things good, do we use the arguably slower technologies like BTrees? If you remember, BTrees provide a worst-case algorithmic time to retrieve a value. To be honest, while this is amazing on its own, it's not nearly as good as constant time, right? Especially with a lot of entries. Well, there are 2 major issues that if you try to solve them, you can't really without implementing something else. And there is a third kind of minor issue with hash-type data structures for indexes, but this one actually has workarounds that are pretty reasonable. So when doing hash-based indexes, the first trade-off is the entire index must fit in memory. Hash anything does not really like to be put to disk and is slow, and there's no good way to serialize just a portion of it onto disk. Plus, you still need to leave enough room for your database to operate in memory while holding the entire index. This gives your database a very finite amount of room to grow, and this might be okay if you only keep a few large records or accidentally bought too much memory for your server. But if you keep very small records like location data, your index could be almost as large as the data you're keeping. And in general, disk is cheap, memory's expensive. So we don't really like that. The second issue or trade-off that you're going to see, and this is probably the most important issue, it might be easier to understand with an example. Let's say that my database held financial transactions and our index was built off the time of the transaction. The thing is, you can't do a range. Well, you can, but the only way to actually do a range is by trying every viable combination in the range, running it through the hashing algorithm, and seeing if that hash exists. This makes range queries really not feasible and definitely not blazing fast. And ranges are just super common. Think about any join or select you have ever done. So this is a pretty big deal, to be honest, and it's probably the biggest deal breaker of hash-based indexes and why you don't see them used all that much. Now, I said that there was this third thing. What is it? It's minor. You can mostly solve it and mitigate it pretty easily. And it's actually an issue that we mitigate in the next video if you want to see it. When you insert into hash maps and your hashes get very large, you end up randomly needing to rehash on insert because of a collision. And this can really slow down insert times kind of randomly. If you need a video on why you need rehashing, let me know and we can rehash it. Yeah, get it? Again, with our architecture that has a read-only log segments, we get around this issue pretty much for the most part. So make sure you watch that next video where we deep dive into hash maps and how they can be implemented as a database index. Now, in contrast, BTrees don't suffer from any of these issues. BTrees were originally designed to have only a portion of the tree in memory at any one time by its original creators, Rudolf Bayer and Edward McCreight, with the assumption the majority of the index would be on disk. So that solves the issue of having the entire index on disk. Now, I would contend that modern databases keep a lot, if not all, of the index in memory if they are capable of doing that. But it's also nice to have the ability to not keep it all in memory if you don't want to or can't because disk is cheap. Now, what about ranges, the Achilles heels of hashes? Well, with BTrees, and yes, I do mean sorted and balanced, but no, I don't mean binary search trees, we get these leaves that actually lend themselves to doing ranges really well and making range queries. To make it overly simple example, let's pretend this is our simple index. Our primary key will just be some integers, and our simple B-tree index would look something like this. Again, this is not exactly how the B-tree would look, as I simplified it a bunch for this. The deep dive on B-tree indexes will definitely dig further into exactly how this data structure would work. One thing I think is really important to note here is that B-trees, unlike binary search trees, can have more than 2 subtrees. Again, this is just a simple representation. I also don't want to fight about whether leaf nodes are only the bottom level or contain data or not, and if we could call those inner nodes or not. It's not important to these discussions, and to be fair, many in academia argue about it to this day, so yes, I know, and no, I don't care. Anyhow, if we wanted the information for records between 9 and 14, this becomes super duper easy and would only require 4 hops to collect all the data. It does not matter how many leaves are in between these numbers, and the thing is, we don't even have to find the 14 node before we start collecting data. We find 9 first, it happens to be the root node in this case, and then we can start collecting the data onward. This is super duper powerful and super duper blazing fast compared to most other access patterns for reading and ranges. This is why B-trees are considered the fastest index type for reading off disk that supports querying ranges. In the future, once we have implemented a few different types of indexes, maybe we give it a try and see if this really actually holds true. Now, it's not my goal to convince you that B-trees are in fact perfect. If they were, we could stop this video here. They, like most things, have trade-offs. They notoriously have an inserting and deleting issue, as when you insert or delete a value, you have to rebalance the tree. Though, because we're not actually held to only 2 child nodes, there are actually some mitigations that can be used to try and avoid these extra things. Although these mitigations then in turn tend to waste a bit of space or work, they don't get rid of the issue entirely. On top of that, while we can do all of these things and mitigate the majority of the worst things by implementing a few techniques with BTrees, none of these things completely resolve the issue, as the tree will have to be rebalanced at some point, kind of like the rehashing in hashes. All we can do is a lot of work to try and do less work. Yeah, it makes sense. In fact, if we get to that video, there have been a whole slew of different types of BTrees that look to solve just these issues, from the B+ tree that forces all the data to be in the lowest level to what they call the leaves, to the B* tree that tries to densely pack the nodes, trying to save you from the costly splitting of nodes on insert, to the B* plus tree that combines all of the initially what sounds kind of contradictory statements together into one happy little B tree. So yes, there's quite a bit of content here if you want to deep dive on B tree index types or just B trees in general. If you do want it, you know what to do. You know what to comment to spam below. Another issue with B trees is that to leverage them well, it tends to force your data storage engine to adopt a different way of storing data than using the log like we are currently. B trees generally enjoy breaking the database into pages instead of log segments like we have previously done. We could, of course, keep it as a log, but then many of the ways B trees can be leveraged effectively would not work as well. So adopting B trees could change how the database works fundamentally. Again, if you want a video diving into this specifically, let me know. We'll do it. Let's move on. So B trees don't play well with our storage engine, and they have just a small, minor inserting and deleting issue that makes it not as blazing fast to insert into, and it can be a little bit cumbersome. But if hash maps kind of suck, as we can't really do ranges at all, and B trees don't play well with our storage engine and slow down writing, what can we do if we wanted to support ranges in our database and have blazing fast writes? It turns out that this is where SS tables and LSMTrees come in. Now, I have to admit that I'm the least familiar with these out of all the indexing technologies we have talked about so far. But don't worry, stop worrying. I think that even if all of you didn't demand a video on SS tables and LSMTrees, we would have one anyways, because I need to learn this, and I need to learn about them better myself. So what are they? Well, SS table stands for sorted string table, and LSMTrees stand for log structured merge tree. But more on that a little bit later. Anyhow, if you remember right now, our log is ordered from oldest to newest in each file. Not only that, the same ordering is applied to the log files themselves. And this is really important. This is how we know what the correct record is in our log. If this is confusing you, go back and watch the first videos in the series. It's really important. And yeah, it's very important. Now, everything is read-only, meaning we don't delete a record. We just write a new line. Now, there is a very simple in theory, hard in practice change we can do to our log database that would actually let us support ranges in a pretty cool way. It's simple because all we have to do is sort our log file. Now, this brings up a whole host of issues. In fact, just sorting our log files does very little for us without implementing a bunch of other things. Now, before we jump into everything we have to do to actually make SS tables work, and it is quite a bit, it's quite a bit, they're not nearly as straightforward as other options. Trust me on that one. Let's talk about why first, though. As you will see, they don't perform reads quite as fast as B trees, and not nearly as fast as hash maps. Well, what does our database do really, really well right now? It does writes. That's right. Writing, currently, with no changes to our database, is blazing fast at writing data. I'm not joking. There is probably few to no databases that can write as fast as the NullDB currently can. And SS tables and LSMTrees look to preserve this insanely fast write. Because while we have to do a little more work when reading, and maybe a little bit more when writing, mostly we can just write to the log like we have been doing in the past, which is blazing fast. So databases that leverage SS tables and LSMTrees, while it might be slower to read, it might be a whole lot faster to write. So if you have a really write-heavy application that needs a database with only light reads and maybe even delayed reads, these types of databases could be quite useful for you. So how do we solve all of these issues? And actually, now that I bring it up, what are the issues of SS tables and LSM trees? We don't have an index or the ability to even find a record or even know if our record exists in the database. It doesn't make a difference if the log file is sorted, right? What benefit does it bring? Well, let's start with a simple one. Does our database even have the record? This one is actually pretty easy, and there's several ways to solve it, but one of the easiest ones is solving it with something like a Bloom filter. No problem. Now, this does not actually help us with finding the record in the log, but it just tells us if it exists in the log, meaning we could have to search the entire file. This can be solved a few ways, but one of the easy ways is by using something like a sparse index. This even lets us just as easily find a range of values as our logs would be sorted. You can see the pieces are starting to fit together with these. Well, to explain it a little bit better, let's run over to the local library, because honestly, your local library is an awesome example of this type of database. Forevermore, you will look at libraries as SS tables or LSM trees databases with a bunch of little logs inside of it. Those are the books, the logs. It's amazing. I have ruined it for you forever now. You will never look at a library the same again. All right. So we're here at the public library to actually fully understand SS tables and SMT trees, because it actually turns out that the public library is a perfect example of SMT trees and SS tables. Because what happens is each library is a sorted log segment. You can think of it like that. Each library is a sorted log segment. And the thing is, a Bloom filter can tell us if a record exists or a book in a library exists in that library. You can call the libraries or you can check on their website if they have the library. But then you have to actually go to the library, physically access disk, and you have to find the book in the library. And now you're gonna say, how is this like SMT trees or the sorted data on disk? And well, the fact is that once the data is sorted on disk, it becomes quite easy to find. And you can use something like a sparse index. And libraries are actually a really great example of sparse indexes, this way to pretty accurately get close to the record that you're wanting to find. So once we're in the library, to find the book that we're looking for, we have to use their sparse index. So once we're in the file, we're at fiction. So this chunk, this kilobyte of data here, is our sparse index. And if we want to find the fictional book, we're going to have to search through all of these books. But that's okay, because it's only a little bit of books. It should be very quick and easy to find the data that we want. No problem at all. So this is the premise behind SS tables and SMT trees that makes them be able to scale and expand. Their indexes can be small and in memory and be very fast. And it also gives you the ability to find ranges as well. You ready to head back to the lab, bud? Yeah. Let's go ahead and head back to the lab and see what else we can learn. All right, so back in the lab. It turns out that SS tables and LSM trees are really not an indexing technology at all. And in fact, to make them work effectively, you have to combine a lot of things together with a bunch of other technologies like sparse index, BTrees or hash index, a Bloom filter, and an in-memory BTree main log file, and even some other things. So let's review the indexes we've learned about so far. Hash-based indexes are really fast in almost every regard to read and insert, and are pretty much the easiest to implement. But they have some major shortfalls, mostly the inability to find a range. BTrees are faster to read in general than SS tables and LSM trees, as they have no scanning of the file, but they tend to suffer on the insert and delete side of things just slightly. And while SST and LSMT is blazing fast to write, retrieval of the data is not as blazing fast because there can be some scanning of the files. So what is the best technology to use? What are we going to do for the Null database? Well, first, next episode, we're going to implement a hash map index. We will not only do a hash map index, but we will start there, and depending on your interest, implement other database indexing technologies as we learn. Unlike your algorithm class, we don't get perfect problems that are perfectly solved by a data structure. We get real-world cruft with real-world issues. Yeah, welcome to software engineering. With the hash-based index, we should, in theory, see a huge improvement to reading and maybe a little bit slower writing, about 9 to 10 nanoseconds. This is awesome and by far a huge improvement. I mean, going from a worst-case scenario of 60 seconds to a worst-case scenario of 1 millisecond with a 50 gigabyte database is downright outstanding. In fact, with the index, as long as it's all able to be kept within memory, we will always have less than 1 millisecond read, no matter how large the database gets. And that is it, really. Now, I know some of you are going to pipe up and say, Merrick, what about SPGIST, GIN, BRIN, or even ART indexes? My point here is that there are a lot of technologies that try to solve the problem of finding data on disk quickly and easily. Most of them have a trade-off or two that you have to understand when picking your index. Like ART, it seems perfect with no trade-off, except it actually assumes that your data is in memory too along with your index. Not only that, but some we saw with the BTrees were opinionated about how you store your data, meaning that some index types might lend themselves to storing data in different ways. Not that they can't, but they don't necessarily want to. Anyhow, I hope you've enjoyed this quick dip into a very complex topic. Next on Building a Database, we'll actually implement a hash map index. But as usual, if you did not like this episode and do not like learning about database technologies, if you don't want to learn about how LSMTrees speed up the compaction process or about the different types of BTrees, I'm going to need you to hit that like button, stick around, and learn how to implement a hash map index in the Null DB. See you in the next episode. You stand up. I squatted down so you could stand. There we go.